Okay, so today we're going to take a look at triangles and angles, which is the start of chapter 4, section 4.1. And we'll start out with just what the basic definition of a triangle is. Okay, so a triangle is a figure formed by three segments, and the three segments are connecting 3 points that are not on a straight line. Okay, they're non-collinear. If you had 3 points that were on a line and you connect them, you wouldn't have a triangle. Okay, they have to be non-collinear. Okay, so there's an example of a triangle. Okay, there's different ways we can classify a triangle. Sometimes we can name a triangle by the length of its sides, or we can also look at the measure of its angles. Okay, so we'll look at some terms to describe triangles. Okay, the first one is equilateral. Okay, what does that mean? Equilateral. You can almost break it down into two parts of that word and figure out what each part means. Yeah.
All three sides are the same.
Yeah, okay, equal. Lateral is sides. We have all equal sides. Okay, all sides are the same length. Right, how about isosceles? What does it mean if a triangle is isosceles? Jacob?
They have two congruent sides.
Right, so we have two sides that are the same. And the definition we're going to go with is at least two sides are the same. Okay, what does that mean if we put it that way? Saying at least two sides are the same. It's very different than saying exactly two sides are the same. Yep.
An equilateral triangle can be also classified as an isosceles triangle.
Right. If we define it this way, which is the way the book does, technically an equilateral triangle would also be considered isosceles because it also has at least two sides the same length. Okay, depending on what kind of book you look at, sometimes they have exactly two, sometimes they say at least two. We're going with the one in the book, at least two. How about scalene? Brian, do you know what a scalene triangle is?
None of the sides are the same.
Yeah, none of the sides are the same length. They're all different. Very good. So those are the three names you can give to a triangle based on its sides. We also have some names we can give a triangle based on its angles. Okay, what does it mean if you have an acute triangle? About James, do you know what that means, an acute triangle?
All the angles are acute.
Yep, all the angles are acute. And what's an acute angle? It's smaller than what? Smaller than 90. So in an acute triangle, all the angles are less than 90. Okay, next one is obtuse. Hey, how about Ariel? Do you know what an obtuse triangle is?
One of the angles is greater than 90.
Yes. And notice she said one of the angles is greater than 90. Why not two of the angles greater than 90? Yeah, then it wouldn't be a triangle. We're going to learn more about that. How about equiangular? If you know what equilateral means, then equiangular is very similar. How about Alyssa? What do you think equiangular means? Break that down. What's the first part of that word? Equi. What do you think that means? Equal. And what about the second part of that word? Angular. What do you think angular means? Angles. So what do you think equiangular means? All angles are the same. They're all congruent. Anybody have any thought about that one? Say equilateral and equiangular? Any comments about those two? Yeah, they really mean the same thing. If you're equilateral, you're automatically equiangular. You have to be. Because we're going to learn that however many sides in a triangle are the same length, that's how many angles are the same length, or same measure. Okay? So if all your angles are the same, all your sides are the same. So those two always go together. Anybody think of another word here that we've covered that would also automatically apply to a equilateral triangle? It's equiangular, but there's also something else that automatically has to happen. Especially, think if it's equiangular. Think about what each angle would have to be, and there's another word that would describe it here.
All of them have to be acute.
They would all have to be acute. So if you have an equilateral triangle, it's automatically acute, because all the angles are 60, 60, 60. Okay, and how about a right triangle? What's that mean?
One angle is 90 degrees.
Yep, one angle is exactly 90. Okay, so there's all kinds of combinations we can have here. Okay, so when I ask you to classify a triangle, try to be as specific as you can. So you might have, for example, a right isosceles triangle. That's possible. Okay, or you could have a right scalene triangle. All right, there's all kinds of different combinations here. Could you ever have an obtuse equilateral triangle? No. Those two don't go together. That wouldn't make sense. All right, but there's all kinds of combinations. So we'll look at a few. Okay, let's classify a triangle ABC. Okay, the abbreviation, if you want to mention triangle ABC, is you just make triangle, and you name the three vertices. Okay, I think there's probably two words we could use to describe this one. Yep.
Acute and isosceles.
Acute, and why do you say isosceles?
I'm inferring that AC and AB are the same length.
Okay, so it looks like they might be the same length. Unless they're marked, we can't assume that they are the same length. If they want them to be, they will mark them for us. So if none of the sides are marked here as being congruent, then what would that mean?
Acute scaling.
Yeah, this is an acute scalene triangle. So triangle ABC is an acute scalene triangle. Now we've got something a little different here. They are marking a couple sides as congruent. So DF and FE are the same measure. Okay, so what kind of triangle is this? I think it's going to be two words again. Luke?
An obtuse isosceles.
Yes, it's an obtuse isosceles triangle. So triangle DEF is an obtuse isosceles triangle. Okay, any question on that? Classifying a triangle. Could you have an acute isosceles triangle? Is that possible? What do you think? An isosceles triangle where all the angles are smaller than 90.
Yes.
Yeah, you could draw that. Okay, it would be something that would look, well actually, you know what? I think they have one right here. Something like this. There is an acute isosceles triangle. These two sides are the same, and all the angles here would be less than 90. All right, so each point of a triangle is called a vertex. It's kind of like the 3 points on the triangle. Those are called the vertices, if you make it plural. Okay, so A, B, and C are your vertices. If you have two sides that share a vertex, we say that those sides are adjacent. Those sides are adjacent. In a triangle, Is there any way to have a diagonal? A diagonal would be a line segment that connects two vertices that are not directly next to each other. No. In a square, you could. In a square, you definitely have four vertices. And there is a way to connect two that are not next to each other on the edges. Okay, you could draw in a diagonal. But in a triangle, there are no diagonals. Okay, so in triangle ABC, we could say AB and BC are adjacent. Right? In fact, if you name any two sides in that triangle, they are adjacent. Right? And when we talk about opposite, opposite means across from. Okay? So if I want to talk about the side opposite angle B, it's the side that's across from it. Okay? It's the side that does not form the angle in any way. Okay? So side CA is opposite angle B. What would be opposite angle A? What side would be across from angle A? Yep. BC. BC has nothing to do. If you took BC away, you'd still have angle A. Okay, it's the side that's farthest away from the angle. And that's important when we talk more about trig. Okay, in chapter 9 or 10, somewhere around there, we will talk more about sides that are adjacent to each other and opposite each other from angles. Okay, if you have a right triangle, okay, a triangle that has 190-degree angle, the two short sides, those are called your legs. They're the two sides that would form the right angle. That's a leg, and that's a leg. How about the long side? In a right triangle, what do you call the longest side? Yep, Kiara? That's your hypotenuse. And the hypotenuse is always across from the right angle, always. If you don't have a right angle, you don't have a hypotenuse. Okay, so for example, in an equilateral triangle, there's no hypotenuse.
So someone asks you, what's the hypotenuse?
Hypotenuse, it's in an equilateral triangle, right? There is none. In general, the definition is a hypotenuse is the side across from the 90-degree angle, or the right angle. And we always mark a right angle by putting that little square in the lower left, or wherever it happens to be. That's how we tell it's a right angle. If something looks like it's a right angle, you can't assume it's a right angle unless it's marked, like that.
What if two angles are, what if that's not marked, but the other two angles are?
Well, if they did mark the other two like this, then yes. You can assume that that is a right angle because of what all the angles in a triangle have to add up to, and we're going to talk about that. Yep. So if you had this, that's still a hypotenuse. That's perfect.
What shape is the most similar to a triangle that's not a triangle?
A square.
Well, I mean, nothing really. It's hard to compare it to. Yeah.
Not even trapezoid.
Because once you add another side to the shape, it changes everything about the angles in it. For example, you all of a sudden with a square, now you're talking about quadrilaterals. So now you can have sides that are parallel, where in triangles you never have parallel sides. And the angles in a quadrilateral add up to 360, whereas in a triangle they add up to 180. So just adding one side changes everything. It's a big difference. All right. So in an isosceles triangle, we said, and I wanted to make this clear, you can have three congruent sides. And technically you can call that isosceles. Because isosceles just has to have at least two congruent sides. But generally, if it has three congruent sides, I'd prefer you to call it equilateral. That's a more specific name. Isosceles is correct, but equilateral is more specific. But in an isosceles, if you have only two sides that are congruent, those are called the legs. Okay? In an isosceles triangle, the two sides that are congruent, if there's only two, are called the legs, and the third side, that's your base. Okay, so here's an isosceles triangle. The two congruent sides are the legs, and the bottom side is the base. What do you call the three points of the triangle? Those are the vertices. Yep. And one of them individually is called a vertex. Good. Any questions on that? All right. Okay, so looking at that picture, I want to know why triangle ABC is a right triangle. How do we know it's a right triangle? Yeah?
It's labeled.
Can you be more specific?
It's labeled with the right angle.
Right, we have a right angle at angle C. Okay. So angle C is a right angle. That's how you know it's a right triangle. Okay. So as long as you know the definition, which is you have one right angle, it's exactly what we have here. Okay. How do we know it's isosceles though? That's the second part. So angle C is a right angle, and what makes this triangle isosceles? Denver?
Because it has at least two sides.
Yes, can you be a little more specific with which ones?
Side 5.
So how do we name the side?
I don't know, I see a little 5 right there.
So which sides are congruent? Like segment
Oh, A, C, B, C.
segment AC, and which one?
B, C.
BC. Okay. So segment AC is congruent to BC. Right? So this is what you'd have to say. Right? Identify the legs, the hypotenuse, and the base. Right? What are the legs there? In that triangle, Selena?
AC.
Yep, AC is a leg. So let's start by just writing the legs. Okay, segment AC. Anything else? Yep, BC. And that's it. A triangle can only have two legs. Okay, hypotenuse. Well, the hypotenuse is the side we haven't named yet. That's AB. How about the base? So we get the legs, we get the hypotenuse. What about the base? Denver? Mhm.
If the equilateral triangle doesn't have a hypotenuse, does it have legs?
An equilateral triangle?
Does it have 3 legs?
We don't refer to it that way. No, not based on our book. To have legs, it has to either be the two sides that are not the hypotenuse or the two sides that are not the base in an isosceles. Those are the only time we refer to them as legs. Yeah. Okay. What's the base? It's going to have to repeat something we already had. Yeah? The base is also AB. So AB, because it's an isosceles right triangle, AB is the hypotenuse and AB is the base. So one segment can be have more than one name. Hey, any questions on that? Okay. All right, so we're going to look at what happens when you take the sides of a triangle and you extend them, okay, and you make them a little longer. Okay. So what we're looking at here, angle A, B, and C, those are interior angles. They're the three angles that are inside the triangle. A, B, and C. Okay, when you take all of these sides and extend just one end of them, don't extend both ends, just one end, okay, we get to form a new kind of angle. Okay, and that's called an exterior angle. Okay, exterior angles are going to be outside the figure. Interior angles are going to be inside the figure. Does everybody have the top part up to interior angles? Okay. Okay, so I'll show you. Let me make it a little smaller. So down below, that's a diagram showing exterior angles in a triangle. So I extended each end of one of the sides of the triangle. And then what's in yellow, green, and blue, those are exterior angles. Okay, any question on that? What an exterior angle is? Okay, and these exterior angles have something to do with the interior angles. There's a relationship between them. Okay, so we'll take a look at what that is. Okay, so again, here's the diagram for exterior angles. Exterior angles are outside the figure. Okay, questions on that? Anybody think they know what the relationship is between interior and exterior angles? And I'll give you a hint. This angle right here has something to do with this one and that one. The one on the outside has something to do with the two that are farthest away. Yeah?
The one on the outside is, I know it equals 180 because of vertical angles, not
Okay, so the one on the outside, the one in aqua here, that's not 180. But together with the one on the inside, it is. And if you know that the one on the inside and the aqua one add up to 180, and you know that all the ones on the inside add up to 180, that's the way to prove what I'm seeing if somebody is going to tell me.
Those two inside angles actually add up to that. If you add them together, they add up to that outside angle.
Yep, the two, we call these remote interior angles. Remote because they're the farthest away. If you take the two angles that are farthest away, add them together, it will equal the one that's on the outside. Okay? That's the theorem. Right, so we'll get to that. We'll look at that in a minute. But the first thing we'd have to know to prove that is you have to know what all the angles in a triangle add up to. Okay, what do the triangles add up to? What do the angles add up to in a triangle? How much?
180 degrees.
Yep, 180 degrees. So the sum of all the angles in a triangle is 180. All right, we're going to prove that. We're going to prove that all the angles in a triangle add up to 180. Okay, and it's a very easy proof. But to prove it, we not only need to draw a triangle, but we need to draw in an extra line. Okay, one extra line. Okay, and this extra line, when you draw it in a diagram or a proof, it's called an auxiliary line. It's not part of the original picture, but you need it to prove what you're trying to prove. Okay, so here's our triangle. Okay, I'm telling you that this shape is a triangle. That's all that's given. And what I'll do is label, let me label them A, B, and C. So there's your triangle. I want to prove that if you add 1 plus 2 plus 3, you're going to get 180. Now, this proof is tricky because you have to add something in that's not there. So it is tough to figure this out unless you've done this kind of proof before. But I'll show you where you need to add in a line. Right there. And what I'm going to do is I'm going to construct that line so that it is parallel to AC. Why can I do that? I could construct it. We learned at one point how to construct a line parallel to a given line going through a certain point. Okay, so that would be a construction. Okay, so let's write down our statements. Okay, so this time the very first thing that I did, it's not a given. That line wasn't given. I constructed it. That was called the parallel postulate. So my statement is going to be, we need another point to name it. Let's just call that BD. So draw in line BD, so it's parallel to AC. The reason? That's the parallel postulate, or you could say it's the parallel construction. That's okay. If you're given a line and a point, there is exactly one line that goes through that point parallel to the given line. And I just drew it. Okay, next thing I'm going to do is, because I drew in that parallel line, I created a couple extra angles. Let's call them 4 and 5. What do we know about angle 4, 2, and 5? If you add them all up, and this is going to be how we get important part of the proof going.
Their sum is 180 degrees.
Right, they add up to 180. That's important. The measure of 4 plus 2 plus 5 equals 180 degrees. Okay, the reason there? That's the definition of a straight angle. And we've added up all the parts. All right, step 3. Did anybody see other angles here that are congruent? Because keep in mind that BD is parallel to AC. So we have two parallel lines cut by a transversal now. Actually, two transversals, so we're going to say two different things. What other angles do we know are congruent? Yep.
1 and 4.
Yes, 1 and 4 are alternate interior angles. Right? Two parallel lines cut by a transversal. So we'll say, we'll do it formally the way we should. Angle 1 is congruent to angle 4. And what else? 1 and 4 are congruent. Yep. 3 and 5 are also congruent. Now those are alternate interior angles. Is that the theorem or is that the converse? Did we prove that lines were parallel? If we did, that's the converse. If we prove that angles are congruent, that's the theorem.
It's a theorem.
That's the theorem, the alternate interior angles theorem. No converse. Okay, so now the next part, if 1 and 4 are congruent, what do we know about, what does that tell you? If two angles are congruent, it means that what? It's kind of the standard statement that always comes after saying angles are congruent. It's the definition of what it means to be congruent.
Their measures also.
They're measures, right? So the measure of angle 1 equals the measure of angle 4, and that's going to help us out when we look back at step 2. Okay? So 1 and 4 have the same measure. 3 and 5 have the same measure, and that's the definition of congruent angles. Okay, so what could I do with angle 4 in step 2 now? Because of what I just wrote here. I could take angle 4 and do what?
Substitute angle 1.
I could substitute angle 1. Okay. What could I do with angle 5? I could
Substitute with angle 3.
I could substitute in angle 3 because I know that they're exactly the same measure. And that pretty much gives us our proof. So now I have, instead of angle 4, I'm going to write angle 1. Angle 2, I'm not doing anything with. And instead of angle 5, I'm going to write angle 3. And the 180, just keep that right where it is. And that's substitution. So we just proved that angles 1, 2, and 3, which are the angles inside the triangle, they add up to 180. That's the pretty standard proof for how you do that. Okay, we're not going to have to go through that proof again. Now we can use that fact all the time. Now that we know that fact, we can look at the exterior angle theorem, which I'm not going to prove. It is a theorem, so we should be proving it, but it's left as an exercise in the book. So the exterior angle theorem says that if you take the measure of an exterior angle, it will equal the sum of the two interior angles that are farthest away. They're called remote interior angles. So in this case, angle 1 equals angle 2 plus angle 3. Technically, I should say measures. Okay, that's the exterior angle theorem. Okay, so let's see if we can find x, y, and z. Okay, let's start off with z. What two angles would you add up that would be equal to angle z? Yep.
40 and 80.
Yep, the 40 and the 80. And 40 and 80 gives me 120. So there's the measure of angle z. It's 40 plus 80. Okay. How about the measure of angle y? What would you add up to get those two? Yep. Yep, you add the 80 and the 60. And 80 plus 60 gives me how much? Yeah, that's 140. Okay, so in this case, y is 140. And lastly, measure of angle x, that's going to be 40 plus 60, which adds up to 100. So the answer to their question, x is 100, y is 140, z is 120. Let's try this one. Let's make it bigger. This one says solve for x. So we're going to be setting up an equation. And you're going to do the exact same thing you did before, except now it's going to have a variable. What could I put on the left side? Yeah?
65 plus x.
Sure. 65 plus x. And we know that that's going to be equal to, what's going to go on the right side?
2x plus 10.
The exterior angle, 2x plus 10. Okay, from here, we just use our algebra and solve it. So subtract x. And lastly, subtract 10. So how much is x? 55. Yep. We don't have to label it as degrees because it already has the degree symbol there. X is 55. The degree symbol is already in the diagram. Any question on that one? All right. So our last thing we're going to look at. This is called a corollary. So we've talked about a postulate. That's something that's given to you, you don't have to prove. A theorem is a pretty important fact, very useful fact that you have to prove. A corollary, it's kind of in between. A corollary is something that's still somewhat important. It has to be proven, but it's so similar to a theorem we already have, it doesn't deserve to be called a theorem. It's too close to it. So we're going to look at a corollary to the triangle sum theorem. So it's an idea that's so closely related to it, we can't call it a new theorem. It's called a corollary. And the corollary is that the acute measures of a right triangle are complementary. What does complementary mean? They add up to, yep, they add up to two angles that add up to 90 degrees. Why does that have to be true? If you have a right triangle, I'm saying that these two angles have to add up to 90. They have to be complementary. Why? Yeah?
Angle of a triangle equals 180 degrees.
Yep, all the angles have to add up to 180.
So with the right angle being 90, the two other angles have to add up to 90 as well.
Exactly. The right angle is already 90, so the other two angles have to add up to 90, or it wouldn't be a triangle. Right? So this really is just the triangle sum theorem, looking at it in the special case of a right triangle. And the proof is exactly what Jacob said. I didn't write it super formally, but angles A, B, and C add up to 180. Angle B is a 90, so I wrote it as 90. Subtract 90 from the other side. That proves that the two angles that are left, A and C, have to add to 90. Okay, so this will be our last one. So it says we have a right triangle. Let's sketch that. And it says the measure of one of the acute angles is twice the measure of the other. Find each angle. Right, let's start with the angle, doesn't matter which one, because this isn't drawn to scale. Start with the one in the lower right. If I don't know what that angle is, how could I represent it for now? Sure, just represent it as x. Now it says the other angle is twice as big as this one. So what would the angle at the top be? It would be 2x. And what do we know about this angle and this angle based on the corollary I just gave you?
But they both have to equal 90. Like to combine.
Combined, they add to 90. So if you take the one at the top plus the one in the lower right, they have to add to 90. So how much is x? 30. That was in degrees. Okay. So if you wanted to figure out your angles, it would be a 30, 60, and 90. One angle is twice the other. Okay. If you had one angle that was 5 times the other, you could do x and 5x and make sure they add up to 90 in this kind of triangle. All right. Okay, so the homework tonight on page 199 is 10 to 21 all. I think that's classifying a triangle by sides and angles. 22 to 26, just the evens. 31 to 39, just the odds. 47. And on the MCAS, finish up the multiple choice doing questions 7 through 12. And tomorrow we'll do the open response.